Okay. So we're back for week 2 of video discussion. This video is going to be uploading a little later today, and also, as you probably already noticed, it's just going to be me today. Dr. Shackelford had some family stuff that he had to do, so it's just going to be me giving you guys a rundown of chapters 3 and 4 of Mountain Probable by Richard Dawkins, which, will be good and bad for different reasons. I think on the one hand, Dr. Shackelford, having read this so many times, is able to offer some useful perspectives on it from that regard. But I also think that hopefully I have some helpful insights as a first-time reader, like many of you also are, or also seem to be, based on your discussion questions. So good. That's good. And I guess this will just be what it is. I also noticed from the discussion questions that a decent number of people had some difficulties with certain aspects and certain concepts of the book, and I was hoping to possibly maybe clear those up. So hopefully some of you will find that helpful as well, if you didn't already get maybe a better sense of some of that stuff from the Royal Institute Christmas lectures, which I absolutely encourage you guys to watch, especially if you're struggling with the reading material, because that stuff is like, it covers all the same sorts of topics. So for example, a lot of people seemed confused about design and designoid objects, so I wanted to spend at least a little bit of time on that. So designed objects are those that are specifically made, usually by humans, in the sense that Dawkins, uses the word. Designed is something that had, a designer, a person with a specific sort of goal or shape or object in mind, and then they crafted it to fit that, mental image that they had, or to serve a very specific function, or to look a very specific way, like how Mount Rushmore, for example, was carved explicitly to model the features of the, the 4 people on the mountain, as opposed to where designoid objects are just, the simplest way I can put it is just objects that look as though someone made them to look a certain way, or that someone crafted them to serve a certain purpose, but that isn't the case. They appear that way. Designoid objects, and he gives them that name to sort of emphasize the fact that they appear designed but shouldn't be mistaken, which is why he chose that term for them, even if that term might be a little confusing. So yeah, and he uses the example of like the beetle that looks like an ant. No one consciously designed an animal to look like an ant, or to have like an archetypal ant shape. The beetle was produced by natural selection over generations of, the beetles who looked more and more like ants in each successive generation, surviving and leaving behind more offspring, until eventually similar to the example with the reeds that he talks about, where you select for the sharper and more rigid reed until you get one that basically serves as like a knife. Um, you know, Successively over many generations, you end up with an ant or a beetle that looks like an ant. Not because, like in the reed example, you had someone choosing the best or the most ant-like beetles of every generation and keeping those ones. That nature sort of did that on its own. Nature, not that nature does anything. It's just that nature imposes the same sort of force, such that it sometimes produces phenomena, or specifically organisms or animals that appear to be designed, and that's what Dawkins refers to as designoid. So that was, I think, the misconception that I saw most frequently in the discussion forum. So hopefully, I was able to clear that up. But if not, of course, feel free to email me or Dr. Shackelford about anything that doesn't get cleared up for you. I'm more than happy to email back and forth or meet via some sort of video chat in order to discuss some of these things, because sometimes it can help to have someone explain it in person, especially if you have specific questions that you need addressed. Please ask, and I'll do what I can. That said, for the discussion forum next week, I only mention this because I saw a couple of people do it this week, or for week 1, and that's totally fine. But from now on, please make sure that your discussion questions are on the reading material. So questions about the stuff in the book. If you have questions about, the class or any of the assignments or the exam, email me or email Dr. Shackelford. But the discussion forum primarily should be a place for you to engage with other students about the reading material and, fight with that stuff there. So, moving forward, keep that in mind. Okay. So all that being said, I guess we can just jump into it, starting with chapter 3. The message from the mountain. And hopefully a lot of you who had concerns or misconceptions about stuff, and those of you who were like expressing your questions and your confusion in the discussion forums, hopefully a lot of that got cleared up in chapter 3, because I think this is the chapter where Dawkins finally kind of, gets to the point more or less, and explains what his goals are in the book, and also sort of gives more insight into, why he's using this specific extended metaphor of, climbing mountain probable as the basis for this book. And I sort of had the advantage going into this book that I had already seen the Royal Institute Christmas lectures, and in those he sort of lays out in different places why he uses this metaphor for natural selection. And so I didn't struggle with the first 2 chapters as much, because I knew where he was going, even though I totally saw places where people would understandably get confused or hung up, because a lot of that isn't really clear in the first 2 chapters, like why is he talking about this stuff, and what is the kind of difficult to see the forest for the trees, so to speak, or difficult to see where he was headed. But hopefully in chapter 3 a lot of that becomes clearer, or will become more clear once you read it. So he sets up the analogy in the beginning. And let me see if I can do it justice, just explaining it in my own words. And hopefully this will help some people and not just totally confuse them. So basically, he sets up the analogy like you're looking at this mountain, and at the top of the mountain is a complex organism, or the human eyeball, or whatever. It's just something really complex, chemically, structurally, or the human brain, even. You could use that as an example. Just something really, really complicated. And you're looking at it as this very distant sort of thing, and reasonably you're thinking, well, how does one get there from nothing? And that's sort of the question that Richard Dawkins sets up as like the being equal to the insurmountable height of the mountain. If you look at the mountain from its face, like imagine a sheer cliff edge with no footholds, and it's like a mile straight up, and you're, thinking how in the world could you possibly climb that? Like that, it's impossible. And that's, it's where the conceit of the title comes in, Mount Improbable, because it looks, in order to get there, in order to get to the summit, the peak of the cliff, it looks so challenging or unlikely that it seems impossible. But if you go around to the other side of the mountain, there's a very gradual sort of ramp almost of foot trails that lead all the way up to the peak of the mountain, which before had seemed so difficult to get to. Now you see a very clear, gentle, easy path up that, someone with, to keep using the analogy, someone with no rock climbing experience could easily accomplish, walking up this very gradual slope. And then, so to return to natural selection, the way that analogy maps onto natural selection, Dawkins is saying that's exactly what, that's exactly how natural selection sort of works, is that, there was no instant jump from the bottom of the mountain to the top. There was no instant, jump from nothing to the human eye or the human brain or a bird's wing or any other aspect of organic life. It was instead a very gradual process from the very beginnings of life, in which there were just these super simple, I don't want to go too deep into that because the origins of life are kind of a separate issue, with a lot of, separate contention around that. But besides that, starting from very simple organisms like millions of years ago, possibly a couple billion years ago, very simple single-celled organisms that were probably asexual and reproduced by just like cloning themselves. And then you take a very gradual sort of progression from that as sort of the bottom of the mountain, the foot of the mountain, all the way to the top, which is, any complex adaptation you can look at today, and say, well, that's an adaptation, whatever you think is so complex that it deserves, it's a position at the top of the mountain. And similarly, by walking up the gradual slope, natural selection produces very complicated adaptations or body structures in animals, starting from comparatively very simple structures. So you very gradually walk up from single-celled organisms to multi-celled organisms to, simple like underwater like fish type organisms. Well, probably like plants first, but then, from plants maybe slightly more complicated organisms that might be more recognizable as animals, gradually up into amphibians, reptiles, mammals, primates, and so on, sort of gradually up the slope of complexity. Though I don't want to, mislead anyone and say that, a primate is more complex than a gecko or whatever, because that would be inaccurate. But I just sort of mean to illustrate that, there are aspects of different organisms that developed, like, arguably are the prefrontal cortex, which is the frontal part of the brain in humans, is more complicated than that of chimps, and it's more complicated than the one in reptiles, or in our whole sort of central nervous system is more complicated than the one in insects, or our heart, which has 4 chambers, versus the heart of a fish, which I think only has like 2 or something. So there are arguments to be made for the complexity of different structures, even if overall there are aspects of a lizard's structure that are more complicated than aspects of a human's structure, or whatever. Or they're more well adapted is a better way of looking at it. We all reached the same height is another way to look at it. If you sort of look at all the different paths up the back of Mount Improbable as different organisms taking different evolutionary routes, all of us who are still around, all of the species who are still around today, have climbed to the same height. We're all the same height up Mount Improbable, just by virtue of us all still being here. But, we've all taken different paths, hence the differences in adaptations. Sort of, that's the analogy for taking a different path up a Mount Improbable, is that we've sort of acquired different adaptations to get here, or we have inherited different adaptations as a result of the environmental pressures that our ancestors faced. Just another way of sort of looking at it. So I don't know. Hopefully that made any kind of sense whatsoever. And Dawkins continues, and this is still early on in the chapter where he's talking about this, but he starts talking about complexity, and he starts talking about the many ways that people seem to continue. That people seem like even educated people, and he points out physicists in the beginning of the chapter here, like Fred Hoyle, Sir Fred Hoyle, who's a physicist, and similarly educated people who seem to continuously misconstrue different aspects of biological organisms as being too complicated to come about by chance. And Dawkins says, well, of course they didn't come about by pure chance. That's a lot of the argument that he makes in this chapter. And Hoyle talks about the incredible complexity of, specific types of amino acid chains being such a particular arrangement that it's, mind-boggling to think how they could have occurred by chance alone. And Dawkins basically says, well, that's because they didn't occur by chance alone. And before I explain anything further about Dawkins' arguments in this chapter, I think it's best to summarize Dawkins' argument and also natural selection as a whole with the following phrase, which I think is possibly the best, handful of words to use to describe natural selection, because it's so accurate and so clear. And that is that natural selection is random mutation and non-random natural selection. Those two elements make up natural selection. So there's an element of randomness in it, that's correct. But these things, these adaptations, do not occur solely as the result of random chance. The mutations are random, within a certain degree. What aspect of DNA is going to be replicated incorrectly is totally random. And that's what causes a mutation, is some sort of a mistake in DNA replication. If DNA were always replicated 100% accurately, 100% of the time, there would be no mutations. Everything would just be, replicated sort of perfectly. But that's not what happens. And as a result of the random mistakes in DNA replication, there are therefore random mutations, which take the form of different physical adaptations. A slightly longer horn on a rhino, or a slightly darker coat of fur on an animal, or whatever, which may or may not have survival benefits for the animal that has that. And then that's where natural selection comes in, which is not random. In fact, it's very specific about which sorts of things it will basically allow and which things it won't. And in that sense, you can sort of think of it as the gatekeeper to the probably many, many, many random mutations that have occurred throughout the history of organic life on this planet. Many of them were sort of restricted from continuing into the next generation. And that's what's so important about this distinction of natural selection as being random mutation and non-random natural selection, because without that gatekeeping and without natural selection playing the role of, if you think back to the example of the reeds in chapter 1, natural selection is taking the role that you would when you're selecting for the sharpest and firmest reeds to make a knife out of. Natural selection is doing that, but sort of blindly. Natural selection isn't this conscious person, like, this sort of spiritual mother nature that's picking her favorite adaptations and allowing the animals with those adaptations to survive and have offspring. Natural selection is just a word for, which adaptations or which features are allowed to survive or are going to have just that slight competitive edge at surviving. And, a single individual in a group of gazelles that is a little faster and is therefore a little bit better at not getting eaten is going to survive and have more children. Those children are going to be faster runners and also be better at not getting eaten. And that's going to pretty much flood that population over the coming generations until there are no more grandsons and granddaughters of the slower running gazelles. They've been overtaken by the genes of that ancestor, that one ancestor with the mutation for slightly faster running, assuming he or she was the only one with that random mutation for faster running. Eventually, that trait will be ubiquitous throughout the entire population. And then that comes to define the whole species. The whole species, or that at least that whole population of gazelles, is composed of slightly faster runners than they were several generations ago. And on it goes. With each successive generation, whatever sorts of adaptations or features that accrue that give those individuals a slight edge at competing for resources or mates or just it being alive, those are the ones that are going to come to compose the later generations, or their children rather are going to compose the later generations. Right, and so he kind of continues on talking about that and talking about the misconception of both the idea that, you know, there's the misconception that there's this randomness that's somehow responsible for very large adaptations, and also that any like large adaptations sort of appear suddenly. So in either case, he sort of likens that to, you know, we're back at the face of Mount Improbable, and he sort of likens that to, instead of going around the back of the mountain and walking up the gradual slope slowly and very, you know, easily, it would be more like jumping from the bottom to the top in a single bound. And he even says on page 77, like right in the middle of the page and that paragraph, only God would essay the mad task of leaping up the precipice in a single bound. And if we postulate him as our cosmic designer, we are left in exactly the same position as when we started. So, more or less, that's what he's getting at, is, you know, you're right, that is a very high point up there, the human eye or the human brain or whatever, and it would be insane to just, you know, scramble up the front of the mountain or to jump all the way up there in one leap. But that's, you know, there's no reason for it because we have a perfectly gradual, reasonable, believable slope up the back of the mountain. And if you, I think with this book, maybe to put that in context, what he's trying to do is he's trying to make the idea of natural selection more reasonable and more believable by saying that if you, and I don't want this to sound condescending, and I don't think Dawkins does either, but if you actually understand how natural selection works, and if you fully sort of comprehend the mechanics that go into it, it should look like a gradual slope. It should look believable, because if you understand that, you know, natural selection, A, has had billions of years to happen, and that it only needs to happen in extremely tiny baby steps, and that it has had so much time for those baby steps to walk such a long way, then you can see that not only is there a gradual slope, but by taking baby steps up the back of the slope, you can get from the bottom to that impossibly high height up at the top. It doesn't take a miracle. You know, and that all sort of falls into place when you understand the mechanism of non-random natural selection sort of culling all of the individuals of a population. Again, I'm repeating myself, but I hope this bears repeating. Natural selection culls or selects from the group the best of each generation, and allows those to survive and reproduce, and so on it goes gradually, generation by generation, with very gradual improvements, though, you know, no one's consciously improving them. There's no engineer tweaking the rhino to make it better, or tweaking the eye until you get to the human eye, generation by generation, tweaking it. It's just that the ones that aren't as good don't survive. And there are also plenty of points up the mountain where paths stop, and you can think of those as extinctions. Of course, there are some extinctions that were sort of doomed regardless. So if you think of like the mass extinction event caused by, you know, that meteor crashing into South America that wiped out a lot of the dinosaurs, that would be a bad example. But for many other species that went extinct, It was likely the result of them, not producing features that were sufficient to survive, or maybe a predator species just got too good at hunting them and then hunted them to extinction. Or maybe it was a predator species that couldn't keep up and all of its prey got too fast for it or got too good at fighting them off. And so the prey starved to death because no one randomly mutated sharper teeth, or no one randomly mutated better hunting skills, or no one randomly mutated faster running. And so because no one randomly mutated it, no one had a generation of kids that inherited that mutation. And so it didn't spread throughout the population. And so eventually the population of slow-running predators just got outcompeted by the population of faster-running prey, for example. So those are examples of, to keep using the analogy, of paths that may end on Mount Improbable, that don't go all the way to the top where we are and where all other living species are. And you should keep in mind that that is the top of Mount Improbable. That's the current day is as high up as we are and all other living species. Yeah. Okay. All right. Trying to find whether or not it's been about 30 minutes so far. Trying to find out whether or not there's anything else in this chapter that I want to discuss. I mean, I know I hit all like the big points. But I don't know if there's anything I want to... He talks about the bush fire and compares it to, contrasts it rather to heredity. So he talks about a smoker dropping a cigarette on like a dry bush and then the fire spreads. Similarly, a mutation could spread throughout a population, like I've been saying that it could, if it has some sort of advantage. There are two sort of key distinctions there, though, that set them apart. A fire isn't hereditary. Fire spreads, or in this example that he uses on page... God, I just saw it and now I lost it. Page 88 and 89. He uses the example of like a smoker dropping a cigarette on a bush and then the fire spreads, but, the fire doesn't have genes. It doesn't pass on the trait of its fire to its offspring. It doesn't even have offspring. It is a fire that, moves from one patch of dry grass to another. But there's no sort of transmission of parent to child on down the lineage, and there's certainly no selecting force that chooses, the properties of this fire to continue into the next generation, but not the properties of that fire because, it's not as good, as opposed to a mutation which is, of course, the result of a gene, so DNA, being spread from one population or one individual to its offspring. It's a very different sort of process. For one, that mutation, in whatever physical form the mutation manifests, should incur, and most often does incur, some sort of benefit to the animal that possesses it, and then that allows the animal to pass it on to their offspring. And then, because of the way that sexual reproduction works, the gametes of that parent combine with the gametes of another parent during sexual reproduction, and they combine to make offspring that have some sort of combination of the DNA of one parent and the DNA of the other parent. And on average, about 50% of the time, the offspring will inherit that mutation of the parent. So assuming that that mutation allows the parent to have more offspring, each time it has a child, there's at least a decent chance that the child will also have that mutation. So even if all the children don't have, they're not faster runners, if they don't have longer horns or whatever, at least some of them will. And again, if that parent animal is better at surviving and or reproducing, then it's going to have a better chance of passing that gene on because it's going to have more children. So Dawkins sort of sets that up as like the contrast to other sorts of spreading, very different from how a fire, for example, might spread. And if you're wondering, like, why does he need to? I understand how sexual reproduction is different from a fire. I get it. The reason he's taking sort of pains and great lengths to describe that and to contrast those two things is to explain heredity as being an extremely significant and important element of natural selection, because without passing the mutation down, there's not going to be successive generations with that mutation. And also, it has to be coded genetically in the first place. Classic misunderstanding of evolution by natural selection is that, maybe if an animal changes during its life, like maybe if an animal becomes stronger by running around a lot or becomes bigger by eating a lot of food, it's going to pass that on to its offspring. Don't fall for that. Heredity, the reason understanding heredity is so important is exactly to sort of avoid that misconception, because you can only inherit things that are genetic. So if you get a limb cut off, if you gain weight because you have better access to food or whatever, it's not genetic. It's not going to be passed down. If it's coded into your genes that you're a little bit taller, or if by some random mutation you are born without a limb, then you can pass that down. Although probably an animal that is born missing a limb is not going to be as fit for survival as its brothers and cousins and colleagues and whatever. But you get the idea. It's got to be in the DNA in order to be passed down, and that's the point of emphasizing heredity. Okay, I think we can move on. Oh yeah, and then toward the back of this chapter, like on page 97 with the frog with the eyeballs in its throat, and he's talking about like macro mutations or things that happen sort of suddenly. He gets a little into the weeds there, talking about how that sort of thing could happen, if it does happen at all, and whether or not such a thing could ever be advantageous or not. Such a large mutation, or whether, large mutations are usually, on average, bad for the organism that gets stuck with them. Definitely read it and spend some time working through it and fighting with it, if that's something that sort of... regardless, you should read it, but especially, like, if you're interested in that, that's cool, and glad to hear it, but at least right now in the video I'm gonna move past it. Again, read it, but like I'm not gonna belabor the point here, because as long as you understand that on the whole again, you're not making leaps and bounds up the back of Mount Improbable. You're walking gradually, baby steps. Although it is important, I think, to still understand the details of, what exactly is a gradual mutation. And, personally, of course, I'm biased. I think a lot of the stuff that Dawkins talks about as far as, macro large mutations is interesting. But moving past it for now, on to chapter 4, which coincidentally is sort of on that same sort of topic of gradual mutations. And I feel like I can really summarize the main idea of this chapter very briefly and still sort of do it justice, which is that the whole sort of like argument here is that in order to get to what, and even using this is like a misconception, but the sorts of adaptations that we view as a final product, and none of this is a final product, because we're, maybe not us specifically, but other people are going to have children, and other animals living today are going to have children, and they're going to continue to develop in some sort of way, in some sort of direction. Their children are going to have features that differ from their own, and there are going to be new mutations that pop up and spread throughout the population over years. So to call anything like the human eye or the human brain, or what Dawkins talks about in chapter 5, the wing, to call any of that a final product is a misconception. However, the point of this chapter is to look at that end product or end goal, or that peak at the top of Mount Improbable, and understand that that didn't have to come into existence all at once, because each step along the way, from the beginning of a wing, from the vaguest, smallest sort of physical feature that could be called at the beginning of a wing, had to have some sort of adaptive benefit every single step of the way, from the very beginning to, again, the end result. Or, if you take a modern bat's wing, or a modern insect's wing, or a modern bird's wing, every step of the way from the first species to begin to grow like nubs that turned into wings, or arms that gradually began to grow into wings with, like, the skin flaps widening between the armpit or whatever, from the very first mutation that you could say is the beginning of a wing, all the way up until the final wing. Every step of the way had an adaptive benefit for the organism that possessed it. And that also therefore means that, say you had, like, let's imagine an intermediate creature, like a flying squirrel, who has like skin flaps that allow it to glide, and it has a child with a mutation with slightly larger skin flaps that make it slightly better at flying, and like almost give it the ability to like gain altitude like a bat, like that. And let's imagine this is a super slight mutation in this child, this one flying squirrel child. Its parent didn't have it, no other flying squirrel has it. It's a true mutation in the sense of the word that we've been using it. We would imagine that child, that that mutant flying squirrel, is going to be slightly better at surviving, at getting food, and subsequently leaving offspring, than its parents were, and then the rest of its competition is going to be. And sooner or later, that mutation that mutant gene is going to spread throughout the entire population, and again, it's going to end up being ubiquitous. So that in a couple generations, all flying squirrels will be pretty much characterized by being slightly better at flying / gliding than were their grandparents a few generations before. And all of the genes for those less efficient, slightly smaller skin flaps are going to be not present, at least not physically present. There may be some some squirrels who carry the gene but don't express it physically. But physically the gene will be gone, and that's hypothetical. But you can extend it to bats, and you can see how the same thing probably happened at, you just pick any point throughout evolutionary history between an ancient bat that probably looked a lot like a flying squirrel or some sort of flying mammal, and modern bats, and you can imagine the same sort of thing happening with a mutant individual having just a slight advantage over its competition, and then gradually that physical feature gets better and better. And that's not, I don't know if anyone would have this misconception, but just in case, I want to make it clear that you can also, I also don't want to overcomplicate things, but you can also imagine other adaptations evolving sort of simultaneously. So you don't have to imagine that the bat evolved all of its wings and then all of its sonar ability or whatever. Those things could have potentially evolved alongside one another. Potentially. I'm not saying I know that they did for sure, but that those sorts of things can happen. It doesn't have to happen, all at once. And if you sort of think about it that way, it would be sort of silly if that's the way it worked. If an animal had to, gain all of its height in its legs before it then, elongated its face, and then, after that, then it could grow out its tail, and then it could grow its horns, and then now you have a deer. I don't know that anyone actually has that misconception of natural selection, but I just figured now might be a good time to mention that. It's not necessarily how it works. So similarly with the bat, even though it evolved gradually its different abilities like flying and its cave habitat and its diet of bugs or whatever it may be depending on the bat, those different things may have evolved at different times and at different rates, but not necessarily all distinctly from one another. There may well have been a lot of overlap as they gradually grew their wings. And the bat is just one kind of example. I think it's really easy to point at the bat because we do have the flying squirrel, so it's really easy to point at the bat and say, well, look, it's so easy to imagine that animal, on its way to becoming a bat, in its early high school days, back when it was just a gliding thing that ate bugs. Because we have the flying squirrel, and it's doing what looks like the same thing, and it's easy to imagine that in a couple, however many, probably million years, I don't want to say any specific number, in a couple very many years, you can imagine an ancestor of the flying squirrel being just as good of a flyer as the bat, not just confined to gliding any longer. But it's important to extend that sort of gradual mentality to insects and birds as well, who also have wings. And I think that's why Dawkins spends a lot of the first part of the chapter talking about size. So if that threw anyone off, don't worry, I also sort of paused at the beginning when I was reading that, like, where exactly is he going with this? Or, I mean, I knew where he was going, but I didn't know why exactly at first. He opened with that. And to summarize, I think his whole point was getting the reader, to buy that wings can evolve gradually by first saying, okay, let's set birds aside for a second, and let's set bats aside for a second, and let's talk about insects. And let's talk about wing nubs. And a lot of you are gonna say, Richard, man, dude, I don't get how a wing could evolve gradually from a little nub on the back that doesn't even look like a wing. What advantage would that have given to the insect that mutated it, or was born with that mutation? To which he replies in the beginning of this chapter, it takes like zero effort for small things to like get off the ground. Basically, I hope I'm not butchering this. Hopefully this is all making sense. But that's basically his argument, saying, listen, dude, bro, it's not that hard to fly, so wing nubs could have incurred a different sort of adaptive benefit than flying when they first developed, but also look at this wind tunnel stuff, isn't this cool, and see that even very slight wing nubs are indeed able to give some aerodynamic benefit to small flying creatures, or to small would-be flying creatures. So basically he's setting up this whole argument to say that yes, wings can evolve super gradually, and in order to buy the whole Mount Improbable analogy and the subsequent explanation of natural selection and how that works, you gotta buy that anything that we can observe in a currently existing species, wings, eyes, the human brain, any of it, could have evolved super gradually, meaning that each subsequent step backwards, along, like back down the slope, would have been an advantage for the creature who had it. Because if it didn't have an advantage, then there's no reason why it would have gotten passed on, and it should have hit a wall where it stopped increasing to the point where it became a wing that we recognize today, or a human eye that we recognize today, or a human brain that we recognize today. If each individual step along the slope didn't give the thing who possessed it an edge in surviving / reproducing, then it wouldn't have kept going up the slope. I mean, the species may have, but that specific adaptation would have hit a brick wall. There would have been no selective force from natural selection to say, oh, well, that's a better version, that's a better model of the brain or the eye or the wing, so that one's going to have more babies, or that one's going to be better at surviving and therefore have more babies. So that's basically that's the argument, and that's really this whole chapter is Dawkins really trying to sell the gradual argument for adaptations, and the idea that each subsequent tiny, like literally, to put it in literal terms in reference to the wing, each like half-inch of wing that mutated on like a child, so a child that has a pair of wings that are just a fraction of an inch larger than its parents, and that was a random mutation. It didn't inherit those bigger wings. It just was a random mistake in DNA replication that resulted in slightly larger wings, or wings that maybe were wider or shaped just a little slightly bit differently than its parents, but that nonetheless made it a little bit better of a dragonfly or a fly or a June bug or whatever, or a wasp, resulting in that individual having more offspring. Until, as we've explained, or as I've explained exhaustively, it feels like, at this point, resulting in the effect that, those slightly better wings in a couple generations become ubiquitous. And then that keeps happening with each, sorry, that's my cat, with each subsequent tiny improvement of the wing or the leg or the eyeball or whatever it is, all the way up the... Psst, stop that. Hey. All the way up Mount Improbable, assuming they made it all the way up and weren't, they didn't go extinct or weren't cut off or whatever, up to modern day where you see the modern adaptations that you do now with the eye or insect wings or whatever. And then, so he sort of diverges to talk about bats and birds as well to further illustrate that point, and says that, they are somewhat exceptions for different reasons. Exceptions from the, very small organisms having an easier time flying, and therefore wings being able to evolve more gradually, being more believable for them. Because with the mammals, the skin flaps, like very slight skin flaps, could incur a benefit from gliding. Bats don't really, modern bats don't need to glide from tree to tree anymore. They can just fly around. So basically with that, Dawkins is saying, and I think you can sort of grasp the idea that, this adaptation that evolved for one purpose, to glide from one solid object to another, was then sort of, it became good enough eventually to allow for just outright flying that bats are capable of now. And similarly with birds, their feathers likely evolved for a different reason before any of them had, flown. I mean, maybe pterosaurs flew before that, but again, they probably evolved flying more similarly to flying squirrels with elongated skin flaps. But anyway, with feathers greatly aiding in the ability for birds to fly, but those feathers evolved way earlier for something else, like heat. I believe he said it was heat insulation, and I believe, if I'm remembering my archaeology correctly, that's what I've heard most often as well. Is sort of the commonly accepted theory is that dinosaurs started developing feathers way before any of them were getting off the ground, or before they were getting off the ground using feathers. So basically what Dawkins is saying is that for animals that are slightly larger than insects, and still a lot of them were pretty small comparatively, they didn't need to be as small as the insects in order for their versions of wings to evolve gradually, because their versions of wings started as something sort of different and then were sort of co-adapted to a new purpose. With dinosaurs, that being like the feathers and probably other aspects of like the arms that turned into wings. And then for bats, it was like, albeit a very slightly different purpose, gliding, similar to flying, but nonetheless, it was still different. It was still a very different lifestyle, especially if you comparing the flying squirrel to the bat. Those are pretty different sorts of lifestyles. But nonetheless, the proposed theory is that at one point, the gliding bat or whatever got so good at gliding, or it became so well adapted to that it was eventually able to sort of step out from that and begin, or it got so well adapted to the point where it became able to fly rather than just glide. So, okay, I think I've belabored that long enough. I'm sure you catch my meaning. And then, so it looks like I have not read chapter 5 yet. I'm with you guys. I'm just a week ahead. So it looks like he is going to continue this sort of similar argument with eyeballs in chapter 5. So he's basically like, get ready for more of that in chapter 5, I think, because he's going to extend the same sort of reasoning to eyes that he used for wings, is that it is 100% plausible, not only possible, but likely that eyes, just like wings, started off way more simple, and each tiny little improvement on the eyeball was an advantage for the creature who possessed it, and resulted in a gradual improvement of eyeballs in successive generations until you have the more complicated eyes of living species. Okay. Is there anything else? He does talk at the end of the chapter, chapter 4, getting off the ground. Getting off the ground. He talks about other sorts of adaptations that are like built on top of others. So like the lungs and the swim bladder or swim bladder lung with fish, basically talking about other examples of adaptations getting to a point and then being used for a different purpose, sort of readapted. And again, that fits with the analogy, because as he says, I'm not sure if he said it in the book yet or if he said it in any of the Christmas lectures you guys have watched, but something he said that I think really is helpful for me is that you cannot go backwards down Mount Improbable. You can't jog back and then take a different path. You can't, say you're a fish and you need to have, like, you want to have like a swim bladder, and all you have are these lungs, these useless lungs, and you can't walk backwards down to the point where you first started evolving the lungs and then go up the swim bladder path instead. You just build a swim bladder out of the air sac that you already have in your body, if that's what happened. But I mean, it doesn't matter regardless. The point is that you work with what you have. So if it gets to that's true for a lot of different adaptations. You work with what you have, and there are a lot of different examples of animals who have organs or any sort of physical feature or adaptation that is very clearly just, they built a new adaptation on top of something else, just really like makeshift, rickety. If you were starting from scratch, you wouldn't have done that because it's not a good plan, so to speak. But it worked. It was the best random mutation that animal's ancestor produced or came up with. And so natural selection said that'll do just fine. It's better than everything else, because everything else is useless. So just again, an example of that slight advantage, that thing being a slightly better version of whatever else was available. Okay, you win the lottery. You go to the next generation, or your kids go to the next generation, and then their kids, and so on, until you get these, again, sort of makeshift improvements on old adaptations or old organs, cobbled together out of past materials. And so it goes. So you march further upward, uh, on up the back of Mount Improbable, never looking backwards, never back tracing, just straight forward, working with what you got. Natural selection, it doesn't remove stuff to make room for new adaptations. Stuff could get smaller. Sometimes that happens. Sometimes, there's a new child and it has a mutation and it's a lot smaller than its parents. But if food is really scarce in that child's environment, it takes a lot less food to maintain a small body than it does a large body. So that's dwarfed sort of child is going to do a lot better than its big colleagues and big brothers and sisters. So that sort of thing can happen for sure. But, like gradually reducing a lung into nothing and then building a different organ back up from that, or like, getting rid of the lung and then starting to produce gills in place of the lung. No, that's not going to happen. Again, because you need to have each individual improvement or, whatever, each small gradual change has to be a benefit for that child, such that it does better than its competition, or else it's not going to, that adaptation isn't going to continue to improve or go in that trajectory. Okay. I've said about all that I think is worth saying on these chapters. In an hour sort of time frame, or an hour and whatever this ends up being. So I'm going to leave it at that. Yeah, and I will see you next week for the next couple of chapters of Mount Improbable, 3 and 4, or 3, 4, 5, whatever, or no, sorry, 5 and 6, and then either 5 and 6 or 5, 6, 7. I can't remember what it is, but it's on the syllabus. And hopefully Dr. Shackelford will be joining me next week. But if not, you will just have to deal with me again. We'll see what we'll see what happens. All right. That's it for now. Thanks. Bye.